Good afternoon, everybody. Welcome to the Think Tank. This is going to be the last session for Cisco Live 2016, and we're ending it on a very high note. If you are just walking by, I know we have a lot of folks that are registered for this, but we're opening this to all of you. You're welcome to join us here in the Think Tank area. We've got seating on the outside as well as in here. I know some of you have other sessions that you need to get to, but hop in on this for the first 10 or so minutes, however much time you have. We certainly understand it if you need to scoot on out of here and get to the next session. I'm going to start by giving a little bit of information about Tim, and we'll talk a little bit about troubleshooting voice over IP and what he's going to be talking about, and then there'll be time for some question and answer at the very end of this. And Tim's going to hang around for a little bit afterwards as well. If you don't want to have a microphone thrust into your face to ask a question, he'll give you a little one-on-one time. So let me just start by talking a little bit about Tim Titus. He's the CTO of PathSolutions. He's a network geek, and he's proud of it. Before starting his own network troubleshooting company, he spent more than 25 years working for small and large companies in a variety of roles, from network engineer to network manager to network director. Tim has taught college-level networking courses, and he's been a member of Interop's NOC team for a number of years. So in this session, Tim's going to review different troubleshooting methods as well as tools to learn about how to get to the root cause of any voice over IP problem and identify them rapidly. Would you please give a nice, warm round of applause for Tim?
Thank you. So, one of the things reiterating what I found is that troubleshooting the problem tends to take forever. And I figured this is something that frustrated me, frustrates a lot of folks in the industry. So what we're going to do is go through why is troubleshooting so hard, go into some methodologies, go into different tools, what they provide, what they can't provide, and at the very tail end we'll talk about some optimization. So why is it troubleshooting so hard? Well, in many cases the proper methodology isn't used or the wrong tools are employed. So let's go through methodology first. So troubleshooting methodologies, really the difference between a junior level engineer and a senior level engineer is their methodology. You can have somebody that might only have a few years of experience, but they can troubleshoot really well because their methodology, and people look to that person as this is the guy who can get the problem solved, guy or gal. And so I figure let's go through some methodologies. Now we've all seen bad methodology. Maybe we've experienced it, maybe we've done it, but bad methodology is do something to fix the problem. Reboot a device, change a setting, replace hardware, reinstall the OS. These are guesses. Typically there's a lot of floundering that happens because you have a CEO or VP that's sitting there standing right next to you saying, when is this going to be fixed? And I'm hoping you're going to answer 2 minutes from now and not 3. So bad methodology leads to floundering and leads to failure. So let's go through good methodology. Good methodology starts with collecting information. What you are is you're a sleuth. You're looking to see where the criminal is, where the crime occurred, collect as much information about that situation, that event as possible. Typically people don't collect enough information. They'll collect 1 or 2 things and say, oh, I think I know what this is, and they'll jump to a hypothesis of saying, it must be the WAN. And it's like, well, if you collected more information and started to characterize that, you'd end up being able to determine that maybe that hypothesis isn't correct. So if you have a hypothesis and you get more information and say it's just not right, the thing you need to do rather than getting stumped, and this is where a lot of people do get stumped, is go back and collect more information. There's always more clues you can collect. Does this happen to the folks in the Dallas office or only to the folks in the Los Angeles office? Or is it maybe only when, let's say, Los Angeles calls New York with a voice over IP that's going through this one trunk? Does it only happen on Thursdays? All of this information helps to characterize what's going on. So go back and collect more information. This way you never get stumped. Now let's say you create a hypothesis and everything seems to look good. The very next thing you want to do is test the hypothesis. Now, if you test the hypothesis and it doesn't hold water, the first thing you need to do is undo the changes because you don't want a multiple cascade of changes. If you switch out one router and you say, okay, we suspected it was a card on that router that was bad, and you switch it out and it doesn't fix the problem, go back to your known good router because otherwise you're introducing too many variables and you could be creating more problems in your environment. So make sure you undo the changes and go back and collect more information. Okay, let's say that hypothesis works. Great, wonderful, you're on the right path. You then need to implement the fix. This usually means scheduling it with your users, saying, okay, we're going to have 15 minutes of downtime at 11 p.m. tonight, and we're going to get the fix implemented. Beyond that, once you implement the fix, it's important to make sure that the original problem is fixed, but also that you haven't created any new problems. By the way, every one of these boxes I have scars from. So if I'm sharing you some of the scars, some of the pains that I've learned, it's that, I fixed the original problem, said, yay, we're done, and started walking home and figured, wait a minute, I've got 6 other users that are having problems now as a result of this fix that I put in place. So you want to make sure that you don't create any new problems with the fix that you just put in place. Okay, so let's say you fix the problem, no new problems exist, you go home, and you're going to get a call at 2 in the morning because you forgot to do this. That's painful because you're thinking, if I just notified the users, I could sleep through the night. So make sure you notify the appropriate users who are involved in this so that they're not going to wake you up at 2 a.m. and end up complaining about it. Now, the next step is to prevent you from being woken up at 2 a.m. a year from now when you're not even doing that job anymore. You want to make sure that you document the fix. If your company has a wiki or some way of communicating inside the organization saying, hey guys, here's how we fixed this problem, so that a year from now when I'm working in a different division, somebody inside there, they're not going to call me at 2 a.m. and say, hey, how did you fix this problem a year ago? It's all in the wiki, it's all online, it's all in your system. So this sort of methodology can be used to solve any sort of problem, and really, again, most of your energy should be spent in that collect information. Okay, so let's have a sample problem here. So we have a call quality problem that happened between extension 41 and extension 53 at noon between those 2 phones, and you want to solve it. Well, it might be later in the day. It might be 5 p.m. Let's see how we could try and get this problem solved. Let's go through a number of different tools to see what do those tools provide us as far as being able to solve the problem. So we're going to start off with packet capture. So you set up a packet analyzer, whether Wireshark or other solution, on either a span port or a tap port. And what you're going to do is you're going to look at an actual VoIP phone call. The results you get on that sniffer trace, you're going to be able to see latency, you're going to be able to see jitter, you're going to be able to see packet loss. Okay, what does this get you? What this gets you is confirmation of a problem. It's going to say, hey, you've got some latency that's pretty high. Your jitter's also pretty high, and your packet loss, that's definitely going to cause a problem. So confirmation, but you still don't know where the problem's coming from or why. So what is packet capture good for? It's good to confirm that you have problems. It's good to confirm content issues. It's good to confirm application layer issues or determine application layer issues, layers 4 through 7. It's not good for finding physical data link or network issues. It's not good for finding limitations in devices or bandwidth. Okay, let's go on to the next solution. So you have APM, Application Performance Monitoring. Typically, you're going to set up a couple of boxes across the network, and they're going to send synthetic voice traffic between those boxes. What you get from APM is very similar to the packet capture. You're going to see, hey, we have this amount of latency, this amount of jitter, this amount of packet loss. So again, what you have is confirmation of the problem, but no understanding of where or why that's actually happening. So it's good for determining what the user experience looks like, which is really what APM is designed for, but it's really not good at resolving the problem. Let's look at NetFlow. So you set up a flow collector, you end up having an actual VoIP phone call. Your router is going to send a flow record back to the flow collector, and that's going to tell you, hey, we had this communication across the network at this point in time from this IP to this IP using these port numbers, this amount of packets, this amount of bytes, but you don't have any understanding if there was any packet loss. You have no understanding if it was actually good or bad. So NetFlow really is designed to tell you who is using the link, when do they use it, what do they use it for, but it's not good for determining if you have any issues with that. Okay, so CDR analysis. You have a call manager solution. You might have something that pulls CDR records and analyzes that. So that CDR analyzer is going to pull those CDR records after a phone call happened and say, oh, we have a CDR record of what happened with that phone call, and it's going to say, at this time we had a phone call from this extension to this extension. We'll probably have IP addresses as well. You have this amount of loss and this amount of jitter. Okay, that's again another confirmational type of tool. It will confirm, yes, you had a call quality problem. You still can't resolve it. So, user says they had a problem. Yep, you're right, you did have a problem. You're not any closer to solving it because you still don't know where that happened. Okay, let's look at SNMP collectors. Typically people set up SNMP and they'll say, okay, great, I've got a collector here. I'm going to go collect the WAN utilization. We have a phone call, and you can look at it and say, well, the WAN utilization at that point in time was 23% utilization. You have some information about what's going on various small parts of your network, but no ability to really analyze or correlate what happened. So this leaves a lot of folks in the dark because you can track packet loss per interface or device. You can have resource limitations tracked, but you're not going to be able to determine who's using the network or application layer problems. So how do you find the root cause? Let's go through this. So you have the actual VoIP phone call. The first thing you want to do is determine where are these phones plugged into the network. So you're going to check your switches and find out where they're physically plugged in, which switch and which port. The next thing, once you've done this, is find out how does these two devices communicate across the network? Which routers do they pass through? Which switches do they pass through? How is spanning tree set up for sending packets through spanning tree ports? So you're going to want to get the layer 1, layer 2, and layer 3 path map identified between these two endpoints to find out here is how this call would flow through the network. And then the next thing you need to do is log in to every one of these switches and routers and make sure that they are healthy. Make sure that you're not having buffering issues. You're not dropping packets because you've got CPU spikes. So every one of these devices you're going to want to make sure is good and look at these log files. Once you've been able to validate that those are all healthy, the next thing you want to do is investigate every involved interface to make sure that these interfaces have the proper VLAN assignment, they're doing the proper DSCP tagging on them, the queuing configuration is working correctly, you have class-based QoS, you don't have any half duplex or cabling faults, broadcast storms, incorrect speed settings, and you're going to want to investigate this on every one of these interfaces to make sure that they are not contributing to the problem. Now, what's kind of sad is you could spend a couple of hours doing this in your network and go through this whole event and still not find the problem. So if the problem was transient and it was happening earlier in the day but it's no longer happening now, you might not spot it. So this is why it's frustrating for a lot of people to solve call quality problems. They'll say, gee, I've got all of the tools to confirm it, but I still can't solve it because I don't know what happened on the network on each of these link switches and routers at the point of time when the call occurred. So how do you optimize this? What you really want to see is you want to have visibility into every router, every link, every switch in the entire infrastructure. You want all of the error counters. One thing that Cisco does better than any other manufacturer is they put a ton of intelligence into their switches and routers. All of this intelligence, though, tends to be trapped up inside of the device. So if you could have all of that intelligence brought out so that you'd know what's going on, and you had this done on a continuous basis, then if you had automatic mapping and problems identified in plain English, you'd be able to solve the problem in 30 seconds. So effectively what you're looking for is a network-aware, massive correlation engine that will correlate all of the individual things that happen to be able to put those events and say, this is what happened to that phone call across the environment. That's what we've built our solution to do. So what we do is we install on a single server in your infrastructure. This can be a virtual machine or a shared server. We're going to deploy, and within a very short amount of time, we're going to have the entire network infrastructure scanned, and we're going to use SNMP to automatically collect information from these devices. Now, you might be thinking, well, I already have a monitoring solution. Do I need something else collecting this? Well, we're going to be collecting different information than what your monitoring solution collects. We're going to go collect routing tables, bridge tables, ARP cache, spanning tree, LLDP and CDP information, even PoE information. So all of the information that is valuable for troubleshooting. Now, we have all of that information collected, and then we're going to go out and collect the health, performance, and status of every link in the entire infrastructure. This all happens within 12 minutes. That means by minute 13, you're going to achieve total network visibility. Now, what is total network visibility? Well, you're going to get coverage everywhere. And if you think about it, your users hold you to be responsible. Your management team holds you to be responsible for the entire infrastructure. We're going to make sure that you have visibility that matches that responsibility. Secondarily, we're going to continuously collect this information every 5 minutes. That way, if somebody comes up to you and says, hey, 2 hours ago I had a call quality problem, what happened? You're going to be able to answer the question because you know what the entire infrastructure did 2 hours ago. Also, we're going to go deeper than any other solution on the market, and we're going to collect that intelligence that's trapped up on those devices. 18 different error counters of information. FCS errors, alignment errors, runt packets, giant packets, even collision counters that a lot of other products just don't pick up. What we then do is we put those error counters through a heuristics engine that analyzes the error counters and says, here's what's going on in plain English. That way, you identify the problem and get it resolved. We can identify cabling problems, half duplex, duplex mismatch, VLAN tagging issues, jumbo frame misconfigurations, Apple Talk broadcasts, any sort of layer 1, layer 2, or layer 3 issue anywhere in the network, any point in time, now gets a plain English prescription. So here's what happens. You deploy, and within 12 minutes, we'll have your entire network instrumented so that by minute 13, we're going to tell you, here's what your network has been trying to tell you all along using those error counters. That way you can say, oh, didn't realize we had a cabling fault out on port 8 of this switch. Let's go out there and see what's going on. You walk into the user's cubicle and you find out that their desk chair has been backing over their Ethernet station cord 5 times a day. You figure, oh, that's an easy one to spot. Rip the station cord out, put a new one in, route it around their desk chair, and within just 10 or 20 minutes, that problem has been found, diagnosed, and resolved. Now, trying to solve that problem on your own might take hours, days, or weeks just to have you find it in the first place. We figure we're telling you this is what that Ethernet switch already knows and has been trying to tell you. That way you get the problem solved and quickly move on to the next one. Recognizing that your routers are complaining about alignment errors, you call up the WAN provider. The WAN provider says, oops, sorry, we set the wrong frame type on that circuit. They change the frame type, the alignment errors clear up. Solving problems with collisions or a duplex mismatch, that's a 5-minute fix if you know where it is and what you're looking for. So 5 minutes here, 5 minutes here, your network is now perfectly healthy. And again, notice that you spent your time fixing the problems, which tend to be 5 or 10-minute fixes at each of these places, versus searching for the problems, which can take hours, days, or weeks to stumble across. So let's talk about how we do a root cause troubleshoot between any two IP addresses. So earlier in the day, let's say it's 5 o'clock, you're packing your bag to go home, but earlier in the day you had a user that said, hey, I had a call quality problem between extension 41 and extension 53. Here's how you solve that. You put in the IP addresses in our product of those two extensions, and we're going to automatically generate a layer 1, layer 2, and layer 3 path map of the network, showing every link, every switch, every router used to connect those two across the network. Then, we're going to show the historic health and performance of every element used along that path so that you can quickly look at it and say, oh, we can now correlate and say, that call was bad at noon because this one router Ethernet interface was dropping 8% of the packets out of the high priority queue at that time. Thus, you get root cause resolution of the problem and you don't have to do any additional searching. So what I'd like to do is show you a very short demo of the solution so that you can see what this looks like. And since I'm an old guy, I need reading glasses, so my apologies here. So here's the product, and you install, and within 12 minutes, it's going to scan through your network, find all your switches, routers, gateways, anything that communicates SNMP. We're going to automatically pick up error counters. In a very short amount of time, we're going to start telling you about problems. So we've got a red dot on the Pinot switch. We can click into that switch. We're going to see all the interfaces. We've got a red dot in front of fast Ethernet 0/2 and 15% packet loss. Now, the first thing most people think about is, well, so what? You found packet loss on a switch port. That's probably the Xerox photocopier. Maybe that's the shipping and receiving desktop PC. That's a low priority problem. On the other hand, if this is the trunk port to the switch, or if there's a voice gateway or somebody's phone plugged in here, that's a high priority problem. So to help make the determination of what this affects, we have a fully integrated port mapper. Click on the Connected tab, we're going to tell you what's connected here. We've got one MAC address. That means there's a single device connected and it's not a trunk port to another switch. That single device associates with our voice VLAN, which is VLAN 82. We see the MAC address here. We can see the manufacturer as well. We have the IP address here, and we can see what the actual DNS name is just by clicking on it. And we quickly realize this is our Santa Clara voice gateway. Now that we know what's affected by this packet loss, let's go see what it is. We click into the interface. We're immediately presented with the daily utilization and the daily packet loss graph. If we scroll down, though, we're able to see here's the plain English prescription of what the problem is. In this case, the heuristics engine is diagnosing this as a cabling fault. So at this point, we can go and get the problem resolved. In some cases, though, you might be wondering, how do we identify a cabling fault through SNMP? Well, if you go up and click on View Advanced Stats, it's going to open the page up. And now we're going to show you all 18 of the error counters that we're analyzing. And if you have FCS errors and a complete absence of alignment errors and an absence of any collisions, you're typically dealing with a cabling fault. But if you had FCS errors with alignment errors but no collisions, then you'd be on the full duplex side of a duplex mismatch. If you have FCS errors, alignment errors, and collisions, then you're on the half duplex side of that duplex mismatch. So it does automatic interpretation so that you don't have to go crack open books to try and find out what the heck do these error counters mean. Now let's put this all together and do a root cause troubleshoot. So I'm going to go to the Path tab here and get my demo here. So from this phone to this phone, we had a call quality problem. This doesn't have to be phone to phone. This can be PC to server, phone to gateway, any traversal of the network. What we're able to show is here's that phone. It's plugged into the Pino switch, connected to fast Ethernet 0/15, and over the past 24 hours, it looks perfectly healthy. Perfectly healthy meaning perfectly healthy according to all 18 error counters. So we can be confident that this is not causing the problem. Outbound, it's going out through fast Ethernet 0/7, also perfectly healthy. Inbound and outbound on the Denver router looks perfectly healthy. Whoa, looks like outbound on the New York router we're dropping a sporadic 1% packet loss. But if we look at this, from current, 2 hours ago, it was dropping 3% of the packets. Since that's when that user complained about that call quality problem, their call was traversing that interface, this is immediately a suspicious interface as to what's causing the problem. So, go click into the interface, read the plain English prescription, get it resolved. But then keep researching because that might not be the only problem. As we keep going, we see that inbound on the Bordeaux switch at the same time, we dropped another 1% of the packets, and that's running half duplex. That's an easy fix. Keep researching. Now we come up to the MPLS router. Now, something you guys might not have been aware is, with your MPLS provider, if you ask them, they will give you SNMP access, SNMP read-only access to the Edge CPE router. If you have SNMP access to that router, you can query all sorts of things. Since we can automatically query the class-based QoS configuration on it, we're going to be able to show you. In this case, we have 2 queues on that outbound interface, a high-priority voice queue and a default queue. Without any configuration, we can tell you there's a problem with that high-priority voice queue because you have no utilization of that queue. All of your voice traffic is dropping into the default queue. That's bad. Let's find out why. You click into the interface and scroll down, we're going to see that queue. So here's the queue, and we can see it's matching DSCP EE45. It should be matching EF46. So that's how we can look into every link, switch, and router queuing configuration involved between any 2 IP addresses to give you a root cause troubleshoot in plain English. So at this point, what I'd like to do is finish up the presentation and remind you guys don't turtle your network, and I guess open it up to questions that you guys might have. And I think they have a microphone that they can walk around and answer questions.
Thank you. Who has a question? Anybody?
Do you guys also deal with wireless?
If the wireless is configured for SNMP, we can pull information off the access point as well and be able to tell you, here's what's going on with that. I'll share a really short, quick story I have about one of our customers that had their access points monitored by our solution. They'd find that the radio transmitters would end up showing 2 to 3% packet loss on pretty much all of their access points, and that's about normal. You're going to have some amount of packet loss. But they found one of the access points had these strange spikes that went up to like 20 and 30% packet loss at different times of the day. And they just walked out and took a look at that access point and figured, what's on the other side of the wall where that access point is mounted? And they're like, well, that's the elevator shaft. They opened the elevator shaft and realized, oh, that's the high voltage AC bus that drives the elevator. So they were able to pull it off that wall, move it to the other wall, and say, problem solved.
We have a question here.
Yeah, so if you're doing an SNMP pull on every port for all that information, do you see high CPU on those devices that you're pulling?
excellent question. With a lot of products, you can do that. I think everyone's heard of the old moniker of the fact that you can crash your network with HP OpenView if it's misconfigured. So what we've done is we put a lot of effort into our packet optimization. What we have is we have a single SNMP packet that we will send out to a device, and we're going to collect 28 different OIDs with that single packet. So we send one packet per interface. So you have a 48 port switch, it's going to be 48 packets out to that device, 48 packets back, but we're maximizing how much information we collect so that we're not sending a flurry of packets on the network. Also, we use a single thread to collect the information. That way we're not overloading links or saturating the CPU with requests. We figure we have a 5-minute window to be able to do a very slow methodical poll to say, give us this information. Got it? Give us this information. Got it? And so with a very slow poll, it keeps CPU utilization low on devices and also keeps bandwidth utilization low, so you can actually query an amazing amount of information across extremely bandwidth constrained 64K links.